Our next presentation is titled Scalable Neural Network Processors for Embedded Applications. Your presenter is Pulin Desai, Director of Product Marketing at Cadence, a longtime associate of mine. So Pulin is going to talk about the architecture of Cadence's latest Tensilica-based neural network processor IP, illustrating how easily different neural networks can be run on it. Pulin?
All right, thanks everyone for coming. So let me start with what I do, where I come from. So I'm from Cadence's IP group. Within the IP group, I am in the Tensilica processor and DSP IP business. Our customers ship about 4 billion plus processor IP annually. We are, in terms of DSP IP licensing revenue, we are number one. Our hi-fi audio IP is the number one choice for a DSP audio IP. I come from Vision DSP IP side of the business. So our Vision P5, Vision P6 are the product DSP IPs that gets used wherever there is a camera path. So if you have a camera being used in automotive, in mobile application, in surveillance application, where you want to do any kind of image processing, or if you want to do any computer vision application, then our customer use our Vision P5, Vision P6 IP. And today, out of the top 5 mobile AP, 2 top mobile AP application processor supplier use our Vision P IP. In fact, MediaTek uses our mobile Vision P5 IP in X30 processor today, application processor today. Also, if you look at our Tensilica's business, out of the top 17 semiconductor companies, we are in top 20 semiconductor companies. So that's enough advertisement about Tensilica and Cadence, and I'll move on to the real topic. Let's talk about some of the trends in the CNN development. So if we take a look at the ImageNet competition, where people have been submitting this AlexNet, Inception, ResNet. So in AlexNet going from 0.7 gigamax per image to ResNet going to 11 gigamax per image, the computation capacity has increased by approximately 16x in less than 4 years. Also, if you take a look at this networks, the AlexNet using a larger, bigger convolution, Inception version 3 using smaller convolution. Also, a number of layers the AlexNet was using, 9 layers versus the ResNet using a much large number of layers. Plus, these networks are also, how the neural networks are being used in classification networks, in semantic segmentation, in deconvolution. So the bottom line is that this whole neural network architecture is changing, and I'm sure you heard a lot of things about that we are in a changing world. The world was changing last 4 years, and it will continue to change. And not only it's changing, but it's also we are trying to create an IP that is going to get used in all these different market, in automotive, server, home, in mobile, in surveillance market. So we are, as an IP suppliers, in 2017, we are working with SoC suppliers who are developing SoC for 2019, 2020, or in some cases 2021. And these SoC suppliers are developing SoC for embedded inference market, where they have to not only look into this changing market, but they also have to look into the low power requirement for this embedded inference devices. Now, if you take a look at the neural network workload by end market, so we try to look at it saying, okay, if I take a look at on the left hand side, you are looking at required gigamex for going from 200 gigamex to multi-teramex, and then on the low end over here at the mobile side, say maybe you are looking at 200 gigamex and maybe running a single convolution on it. And in this case, let's say it's like your GPS that you are using neural network once in a while, like GPS get used once in a while. But when you use the GPS for 20 minutes, after 20 minutes, your battery has run out. Well, you don't realize it because you are always plugged into the power. The same way, if you are using a neural network only for a short time, you still want to make sure it's very efficient while it's running on your mobile phone. And as you move up into a surveillance camera, where maybe you're looking for a 1 teraMAC, but now instead of using it once in a while, you are using it all the time. The camera is on all the time. Now, instead of one neural network, maybe you are detecting multiple objects, and now you do need more than 200 gigamex per second. You might maybe looking for a 1 teraMAC, and then you move up. Instead of a few neural network, you might have 10, 13 object that you are trying to detect for this autonomous type of application, and now you will need a multi-teraMAC type of a solution. So now let's take a look at what's available today. So we try to take a look at for an embedded solution, what's available. Well, you have CPU, you have GPU, you have neural network hardware accelerators, and then you also have imaging and vision DSP, such as what we provide, our vision DSP. And then we try to take a look at it from ease of development, power efficiency, future proofing, and the neural network performance. And over here, white is good, red is bad, and blue is maybe okay. So if you take a look at from the ease of development, the CPUs, that's easy, pure software solution. They are good tools like this laptop or any other CPU that you might be using, off-the-shelf IP, so it's very easy to develop. GPU, again, it's ease of use, pure software development. It's easy to develop. Same thing for imaging and vision DSP. It's easy to develop. It's a pure software solution. Now, in terms of neural network accelerator, it's difficult, we believe. It's because what you are doing for a neural network accelerator is that you are developing a fixed hardware. You are developing something that is fixed at the tape out. And software may be partitioned between your accelerator and maybe the imaging DSP that you are using. And so it's not very easy to develop that solution. In terms of power efficiency, the CPU is always going to be bad. Compared to CPU, we gave it a blue because compared to CPU, the GPU is going to be better, but it's not going to be as good as the vision DSP. And in terms of hardware accelerator, great for offload layers. So if you are offloading the convolution layer, maybe it's good, but not all other layers. All other layers, you are saying that I'm going to run it on the companion vision DSP. In that case, it may not be good. Plus, you have a lot of data movements that's going on. In terms of the future proofing, CPU, GPU, vision DSP, they are good because, well, it's all fully programmable. But for a neural network hardware accelerator, it may not be good because you have built a purpose hardware. It's a high risk, saying, okay, this is what I want today, I'm going to build an accelerator for that today. It's not programmable. And as I described earlier, we are living in a changing world. The neural network stuff is being still changed, and a lot of PhDs are working on it today. So if you are building a hardware accelerator, you fixed your architecture today, maybe it's not future proof for it. In terms of performance, CPU, I mean, it's anybody's guess. It depends on how many cores you have. So I put it 200 gigaflop. In terms of GPU, well, I'm not talking about your high-end GPU. This is a GPU that you may have integrated in your SoC. So we said it's about 200 gigaflops. And then hardware accelerator, yeah, sure, you can develop in a Teramex type of range, so we gave it a white. And then in terms of imaging in Vision DSP, most of the imaging in Vision DSP, including our Vision P6, has 256 max, so it's about 200 to 250 gigamax type of capacity. So after stating this problem statement, now I would like to move on to the new product that we introduced, Vision C5 DSP for neural networks. This was announced yesterday, so let me move on to that. Vision C5 DSP for neural network. What is it? Well, with Vision C5 neural network, we are introducing a brand new category called neural network DSP. It's a complete standalone DSP that runs all layers of neural network. It runs convolution layers, fully connected layers, normalization, pulling, you name it. Anything related to neural network, you run it on this DSP. We are building a DSP for the changing neural network field, general purpose and programmable. So as I established earlier, we are living in the changing world, and this market will continue to change. So we are building a programmable and general purpose a DSP that not only will address today's market, will also address a future market. Also, it is not a hardware accelerator. It is a programmable DSP dedicated to normal neural network and optimized for neural network accelerator. And we'll talk more about it, because what we did, that we looked at the problem ground up and say, how do we build a neural network DSP? And that's what we built. It is architected for multi-Teramex solution. And then same proven tool set as Vision P5 and Vision P6 DSP. So Tensilica has been in business for over 17 years. We have good software tools that our customer has been using, our assembler, compilers, instruction set simulators that's been used for a long time, and same tool sets were used for our Vision P5, Vision P6 DSPs. And because this is a full DSP, the same tools will be used by our customer with our Vision C5 DSP. Some more information. This is a block diagram. This is a DSP IP that sits on AXI interface. It has instruction memory, it has data memory, it also has a DMA on it. So from outside, it looks like maybe all our DSP, but then the inside, under the hood, we did a complete surgery. As I said, we did a ground up design where in terms of the processing capacity, it is 1024 max. So in terms of the Mac, it is 4x more Mac than the Mac capacity we had in our Vision P6. It is 128-way 8-bit SIMD architecture, plus all other things that you would need for the neural network processing, like on-the-fly decompression, flexible instruction set for quantization. So here, as you know, you would be training your network on the servers using GPU. So you will get your network coefficient and network information in floating point. So you need a good quantization support. Plus, we also have quite a few optimized instruction specifically for neural network. Some more information. We already talked about 1024 Mac for 8-bit. We also have 512 Mac for 16-bit. This is a 4-way VLIW machine, 120-way 8-bit that we talked about. Integrated DMA I talked about, plus it has the industry's widest memory bus, 124-bit interface that you are looking at. And then in terms of the area, it's basically giving you one Teramek in less than 1 mm square. So now let me move on to some other comparisons. So you're looking at a diagram, a typical diagram. I have not gone into a lot of detail, but if you are building a system, you might have a system where you have CPU, GPU, memory controller, I/O, and camera subsystem. And then you might already, if you have a camera subsystem, you might already have a Vision P6 and Vision C5 DSP. So in that situation, a neural network accelerator will look like the same thing. That at the high level they both look the same. But for a single processor system, they both look the same. But for for how they both run the neural network, that's the big difference, and how the multiprocessor system is built, that's a big difference. So let me kind of walk through some of the differences. The Vision C5 is a complete neural network processor. It runs all layers. We already talked about that. Now the other thing is that it's a flexible and future proof. So it supports variable kernel size, depth and input dimensions, supports different compression decompression techniques, support for new layers can be added as they evolve. Hardware accelerators are mostly designed based on current needs and hence provides a rigid and not future proof solution. Main vision imaging free to run on other applications while neural networks run on neural network. While running neural network, main vision imaging DSP cannot run other application. You are basically stuck with both of them running this neural network thing. In terms of programming matter, Vision C5 neural network DSP, it's a single programming model versus in neural network accelerator, it's a complicated programming. You have two processors you have to program. No need to move data between neural network DSP and the main vision programming versus in the other cases you have to move the data between two of these things. So the other way to look at it over here, that you have convolution layer, you have a max pooling layer. You run the convolution layer on accelerator and you run the other thing on the vision DSP versus in our case entire neural network runs on the Vision C5 DSP, no extraneous data movement and does not occupy the imaging in DSP while you are running neural network. So let's couple of slides we'll talk about the multiprocessor system. So we have built the multiprocessor system for the last 17 years on our Extensa stuff. So we provide all the necessary infrastructure to build a multiprocessor system like shared memory architecture, interrupts and queue for synchronization, automated creation of multiprocessor system, and synchronous multiprocessor debugging. So our customer can build a multiprocessor system with this ecosystem that infrastructure that we provide. Now, if you move on to a multiprocessor system for comparing to a neural network accelerator, in our case, you just need to put the multiple Vision C5. So Vision C5 DSP scales elegantly versus a neural network accelerator. You will have to put not only a Vision DSP, but you will have to put a neural network accelerator. So both the cores has to put multiple time, and that increases area and power. So in terms of performance, Vision C5 compared to a commercially available GPU, AlexNet performance up to 6x and Inception version 3 up to 9x. At both of them running at the same clock rate. So coming back to the same table here, Vision C5 ease of development, pure software programming, power efficiency optimized for neural network, no wasted hardware, no wasted data, no data movement. Future proofing, yes, always reprogrammable. Maximum performance 1 TB. So now you got all this wonderful DSP, you need some ways to program it. So if you have already done your training on a neural network using a Caffe or TensorFlow, then we have this neural network mapper that will convert, do the quantization and create the code using our neural network library to run on a Tensilica Vision C5 DSP. So essentially a push button way to bring from a TensorFlow or Caffe to our Vision C5 DSP. And then we have worked with all these software partners with our Vision P5 and Vision P6, and then those partners are familiar with our tools, those partners are familiar with our instruction set, and those same partners will be able to work with us on the Vision C5. And, we are a member of Kronos Group. We are actually, in fact, chairman of OpenVX working group. 2 weeks ago, we announced OpenVX 1.1 compliance for our Vision P5 and Vision P6. In fact, we are the first Vision DSP IP to pass OpenVX 1.1 compliance. In fact, we have OpenVX 1.1 demo running in our booth over here. Just so coming back to the original chart, so with the introduction to Vision C5, with Vision P6 and Vision C5, basically we can address all the market segment that I defined earlier. So in summary, Cadence Tensilica Vision C5 provides first complete standalone DSP IP to run all neural network layers. 1 TB in less than 1 mm square, general purpose and programmable. It's a complete DSP. Scales to multi-teraMAC, and we address all these markets: surveillance, automotive, drone, mobile, whatever you want. Thank you.
Pulin assured me that he could get through all those slides in 20 minutes, and I didn't entirely believe him, but he did it. Thank you very much.
People do tell me I talk fast, so hopefully you understood me.
Any questions from the audience?
Hi, you quote 1 teraMAC in less than 1 millimeter squared. What process is that?
Yeah, there were 2 stars in one slide. You, I guess, didn't see that. 16 nanometers. I'm just joking.
Thank you.
Other questions? I've got one. So,
Sorry, before you say, I told Chris not to ask any questions, so he didn't ask any question. I'm sorry.
Chris, do you have any questions for him? You do, but you're behaving yourself. So, last year at the show you announced Vision P6, right? And so you have a DSP core that's capable of doing both classic vision algorithms and some level of deep learning. Obviously, to do an incremental project that's very deep learning focused, right? That takes manpower, that takes time, that takes effort. You obviously had an expectation that this was a substantial market that you could target, and there would be a solid return on that investment. In addition to marketing the existing products, you're very involved in defining new ones. Can you talk about the thought process and the dynamics that went into that decision?
Yeah, it's a great question. So obviously we do believe that there are opportunities for a dedicated neural network processor. That's why we developed it. There is a couple of things happening in the marketplace that no matter what happens, and you probably saw over here that neural network is a new thing, and we all talking about it. So there's a lot of things going to happen in neural network, but imaging does not go away. Imaging is here to stay, and we will continue to make a lot of investment in imaging, and that product line will continue to be there. But at the same time, the neural network is in a new area that's expanding. So what we are seeing that it's that, and that's why in one of the block diagram I showed that there is a imaging DSP and there will be a neural network DSP. So in an SoC we see opportunity for 2 things: imaging DSP and a neural network DSP. So if you say I want to do imaging, do that on an imaging DSP. If you say I want to do neural network, do that on a neural network DSP. That's the way we look at it, and we see a lot of those opportunities in automotive market. We see that opportunity in the mobile, in the surveillance market, and eventually in the mobile market. So don't go and add something so that you take away your imaging DSP to do the neural network. Now, sure, right now imaging DSPs are available, and you might be doing some neural network for once in a while, but we eventually see those things separating into 2 DSP on an SoC.
Separating out from an application standpoint, but I'm assuming that in a lot of applications they'll end up being multiple cores from your company on the same SoC, one
That's
doing
correct.
ISP functions.
That's correct.
And a downstream one doing deep learning on that, right?
That's correct.
Okay. Comments or questions? Okay, we're going to take, you got one more. Go ahead, sorry. I didn't see you moving.
Just one question on that 1 teraMAC per second. What power is that?
So we're not, disclosing the exact power right now.
Okay.
On that will be low power.
I'm sure. Okay, thank you.
And for more information, catch you at the break.
Yeah, so I didn't show you, so you can find more information on ip.cadence.com, where you can find the data sheet of this product and all the announcement here.
Okay, thank you very much.
Thank you.